Hi everyone and welcome to this first video about the reduction of alkenes to alkanes. This presentation is about the heterogeneous catalytic hydrogenation of alkenes. This is a valuable reaction because many C-C bond forming reactions yield alkenes. These include condensations and carbonyl olefinations. Then, crude oil contains olefins and arenes that can be converted into useful intermediates by catalytic hydrogenation. Hydrogenation is also well suited for large-scale industrial preparations because it does not generate any waste and hydrogen is relatively inexpensive. In part 2 of this playlist, we'll have a look at catalytic hydrogenations with the aid of soluble catalysts, mostly rhodium, iridium and ruthenium complexes. Part 3 is about the reduction of alkenes without the use of hydrogen, for example with the aid of hydrogen-generating reagents or with various hydride donors. Within this playlist, only the reduction of olefins is discussed. On my channel you can also find a short playlist about the hydrogenation of arenes, which usually requires different catalysts and harsher reaction conditions. Cyclododecane is one product of large-scale catalytic alkene hydrogenation. The starting triene is obtained by cyclotrimerization of butadiene, and the main application of cyclododecane is the preparation of monomers, for instance a C12-dicarboxylic acid. Hydrogenation of butenediol or maleic anhydride are used to prepare butanediol, THF and butyrolactone. Then, hydrogenation of aldol condensation products is an important strategy for the preparation of saturated ketones and alcohols. These are used as solvents in paints, glues, coatings and related products. As an example, I've sketched here the hydrogenation of mesethyl oxide, the first self-condensation product of acetone. One of the most common catalysts for catalytic hydrogenations is 5% or 10% palladium on charcoal, which is prepared by reducing palladium-2 salts in the presence of charcoal. The commercial catalyst usually contains some water and is not pyrophoric, but can catch fire at the air when wetted with some organic solvent. It may also ignite spontaneously upon contact with vapors of a volatile hydrogen source, for example cyclohexadiene or formic acid. To prevent fires, the catalyst should be added to the nitrogen or argon-filled reactor first, followed by the solvent and the alkene, and then by any optional hydrogen-releasing reagent. Separation of the catalyst by filtration once the hydrogenation is finished is again potentially dangerous. I always use cellite to filter off palladium on charcoal and never had any fires, but ignition is possible when the dry catalyst comes into contact with air and solvent vapors. For this reason, used catalysts should not just be thrown into the garbage, but better be kept under water in a separate container. Garbage fires and explosions are the most common accidents in the chemical laboratory. And during my 30 years in various laboratories, I've had a few of these. A slightly less active catalyst is palladium on calcium carbonate. The so-called Lindlar catalyst can be used to hydrogenate alkynes to cis-alkenes. Alternatively, palladium on charcoal may also be deactivated by some amines, pyridines or thioethers. Much more pyrophoric than supported palladium is ranitidine. This catalyst is prepared by dissolving aluminum from an aluminum-nickel alloy with aqueous sodium hydroxide. Ranitidine is then isolated by decantation and repeated washing and decantation with water, ethanol and then with THF. Filtration is no option because freshly prepared ranitidine immediately ignites when dried in the presence of air. Because upon dissolution of the aluminum, hydrogen is formed, freshly prepared ranitidine is already saturated with hydrogen and can bring about hydrogenations even before placing the reaction mixture under hydrogen. The initial high reactivity of the catalyst drops, however, upon longer storage. Platinum oxide is also a powerful catalyst for hydrogenations. It is reduced to elemental platinum by hydrogen and shows a slightly different selectivity than nickel and palladium. Also palladium may be used in the form of its oxide, but the supported versions of palladium are more convenient and normally preferred. Palladium and platinum oxide are also strong oxidants and can cause some unwanted byproduct formation. Copper chromite is similarly inexpensive as Raney nickel but much less reactive. Hydrogenations with copper chromite often require temperatures above 200 degrees Celsius, and this catalyst can also bring about decarboxylations and the hydrogenation of carbon-oxygen double and single bonds. Alkenes can also be hydrogenated with supported rhodium, ruthenium, and iridium, but these catalysts are mostly used for the hydrogenation of arenes. Cobalt, copper, and iron-based catalysts are similarly unreactive as copper chromite and often require a high reaction temperature and hydrogen pressure. This low reactivity implies a high selectivity, which can be valuable for certain polyfunctional alkenes. In general, though, these catalysts will require harsher conditions and more optimization work than palladium, nickel, or platinum-based catalysts. The rate of catalytic hydrogenations also depends on the amount of dissolved hydrogen. In general, the solubility of hydrogen decreases when lowering the polarity of the solvent. Upon heating, the solubility of hydrogen in various solvents usually drops. But most modern autoclaves provide for a very efficient mixing of the gaseous and liquid phases, so that gaseous hydrogen will come into contact with the catalyst and saturate it. Therefore, the ability of a solvent to dissolve hydrogen is not as critical as the pressure, the type and amount of catalyst, and the reaction temperature. So, how do noble metals catalyze hydrogenations? The current hypothesis is that at certain active sites on the metallic surface, hydrogen is absorbed, causing a weakening or outright cleavage of the hydrogen-hydrogen bond. Actually, many metals react with hydrogen. Sodium hydride is prepared from the elements, and in industrial plants that must handle hydrogen under pressure, one common problem is that tubing and containers become brittle. Many explosions occurred during the development of the Haber-Bosch synthesis of ammonia from nitrogen and hydrogen, because the reactors couldn't withstand hydrogen at high pressure. I'm skeptical about the future use of hydrogen as fuel, touted by many politicians. Liquid fuels are much safer and easier to handle and can be produced from carbon dioxide. Moreover, the whole infrastructure and know-how for handling liquid fuels safely is in place. During catalytic hydrogenations, the noble metals do not form monomeric metal hydrides, but just reactive hydrogen at certain active sites on the metallic surface. This process is reversible, and often less than 1% of catalyst will be sufficient to attain a high rate of hydrogenation and complete conversion. For hydrogenation to occur, also the olefin must be absorbed on the metallic surface. The metals suitable as catalysts are soft Lewis acids that form weak bonds with the pi electrons of olefins. When this occurs in close proximity to metal-bound hydrogen, the olefin can insert into the metal-hydrogen bond. Alternatively, if the olefin contains allylic CH bonds, insertion of the metal into this allylic CH bond will yield an allylic complex. Because all these reactions are reversible, if the concentration of hydrogen is too low, an isomerized olefin or even a diene may be released into solution. Thus, hydrogenation catalysts can also be used to isomerize alkenes. In the presence of a large amount of hydrogen, cleavage of the metal-carbon bond and reductive elimination of the alkane can occur. Even this step is reversible, and under forcing conditions, metallic palladium or nickel can sometimes cause the dehydrogenation or oxidative dimerization of saturated alkanes. In the presence of oxygen, such dehydrogenation of organic compounds may already occur at room temperature, and is the main reason why these catalysts sometimes ignite spontaneously at the air. The relative rate of alkene hydrogenation is governed both by steric and electronic effects, with steric effects being the most important. The fewer alkyl groups directly attached to an alkene, the faster is usually its hydrogenation, and tetra-substituted alkenes can be difficult to hydrogenate. Then, simple alkenes or styrenes often react faster with hydrogen than electron-deficient alkenes. Enol ethers and enamines also react more sluggishly. Push-pull olefins, that is, alkenes substituted both with an electron-withdrawing and an electron-donating substituent at opposing carbon atoms, are particularly unreactive and difficult to hydrogenate, while the so-called captodative olefins, that is, alkenes with an electron-withdrawing and an electron-donating substituent at the same carbon atom, are again highly reactive and usually undergo quick hydrogenation. Here are some specific examples to illustrate the effect of alkyl substituents. Norbornene is a special case because, despite its poor steric accessibility, the CC double bond is strained and therefore more reactive than usual. The low hydrogenation rate of tetramethyl-ethylene is also remarkable. One common problem of catalytic hydrogenations is poisoning of the catalyst. In such instances, the hydrogenation just will not work, no matter how much catalyst or hydrogen pressure is used. This can be caused by impurities in the starting material or solvent, or may be inherent to the structure of the starting alkene. Hydrogenation can only proceed if the alkene is absorbed at the active site on the catalyst surface. Thus, these sites must act as soft Lewis acids. Most catalyst poisons are therefore soft Lewis bases, that is, compounds that will form a strong bond to Lewis acidic sites on the metallic surface. These include thiols, thioethers, thioureas, and other sulfur-containing compounds, nucleophilic amines such as DAPCO, phosphines, isonitriles, and even some nitriles. Alkenes containing such functional groups can be difficult or impossible to hydrogenate with transition metal catalysts. In the case of amines or phosphines, acids can sometimes prevent catalyst poisoning. Also, chelating ligands can be powerful catalyst poisons, for instance 2-amino alcohols, alpha-amino acids, diamines, amidines, imidazoles, aminopyridines, or hydroxyquinolines. Again, the addition of acids to the reaction mixture can be helpful. Further catalyst poisons include carbon monoxide, cyanide, thiocyanate, and lead or mercury salts or complexes. In short, compounds that form strong bonds to late transition metals may also block the active sites of hydrogenation catalysts. If catalyst poisoning is caused by an impurity in the starting alkene, one possibility is to wash the alkene with an aqueous solution of some copper-2 or iron-2 salt, or to pre-treat the starting material with Raney-nickel. These metals may form insoluble complexes with the catalyst poison, which can then be removed by filtration. Most hydrogenation catalysts bring about a cis addition of hydrogen to the alkene from the sterically more accessible side. Occasionally though, as in this example of transfer hydrogenation with hypophosphite, trans isomers were the main product. As discussed above, hydrogenation catalysts can also cause the isomerization of alkenes. In this instance, because alkenes with 4 substituents are hydrogenated more slowly than alkenes with 3 substituents, product formation occurred mainly through the isomerized alkene. This is, however, not always so. Here, for example, an alkene with 4 substituents cleanly yielded the product of cis hydrogenation in only half an hour at room temperature. Conjugation with the benzene ring was probably the main reason for the enhanced reactivity of this alkene, if compared to the previous example. A large number of functional groups may be hydrogenated by transition metal catalysts. Polyfunctional alkenes can therefore be difficult to hydrogenate selectively. Common strategies to increase the selectivity of hydrogenations include lowering the reaction temperature, adding acids or bases, using non-polar solvents, or adding a weak catalyst poison, such as diamines or diphenyl sulfide. In laboratory preparations, one may also monitor the hydrogen consumption and stop stirring as soon as one equivalent of hydrogen has been absorbed. On the next slides, I'll show you some specific examples of selective hydrogenations of polyfunctional alkenes. These include alkenes containing additional double bonds, halides, epoxides, nitro groups, benzylic ethers, and peroxides. Feel free to stop the video and skip forward to the compounds of your interest. Many examples have been reported of the selective monohydrogenation of dienes. Unfortunately, it is not always possible to predict correctly which double bond will be reduced first. Here, for example, the less substituted electron-rich alkene was hydrogenated faster than the tri-substituted electron-deficient olefin, as would be expected. In this example, however, the selectivity was reversed and the electron-deficient alkene was reduced faster than the electron-rich one. Both alkenes were tri-substituted and a deactivated Lindlar catalyst was used. In this example, it was again the more electron-rich alkene that was hydrogenated first, with impressive selectivity. As already mentioned, styrenes undergo hydrogenation readily. Here, it was possible to hydrogenate a substituted styrene selectively in the presence of an alpha-beta unsaturated nitrile by conducting the reaction at 0 degrees Celsius and for only 20 minutes. In this example, a triene was hydrogenated with amazing selectivity. Such outcomes cannot be predicted and often require a lot of experimentation. Enones and other electron-deficient alkenes can often be reduced selectively with sodium borohydride, zinc, sodium dithionite, or related hydride or electron donors. In the second equation on this slide, the enone was hydrogenated faster than the more electron-rich olefin with a copper catalyst at 90 degrees Celsius. Also, the ketone was reduced to a secondary alcohol. With platinum oxide as catalyst and at room temperature, however, a clean hydrogenation of the electron-rich alkene occurred. This is an example of systematic deactivation of a catalyst and optimization of the reaction conditions to enable the selective monohydrogenation of a diene. Allylic esters are particularly sensitive to hydrogenation catalysts and readily undergo reductive CO bond cleavage. This potential side reaction, as well as the twofold hydrogenation of the diene, could be prevented by adding water and a small amount of a phosphide to the reaction mixture. Ruthenium on charcoal was used as catalyst. In this example, the push-pull alkene was a vinylogous ester. Such olefins are rather stable and difficult to hydrogenate. Thus, the selective hydrogenation achieved here was not really surprising. Even simple enamines are sometimes hydrogenated faster than push-pull alkenes, as in this example. Both the ketone and the benzylic CN bond remained unchanged. This is the only example of the hydrogenation of an enamine in this playlist because enamines are usually reduced by treatment with acids and some hydride donor such as formic acid or borohydrides. On my channel there is a playlist about the alkylation of amines where you can find a more thorough discussion of the reduction of enamines. As mentioned, norbornenes are strained and more reactive than most other alkenes. It is therefore difficult to predict the order in which the double bonds of a norbornene-containing polyene will be hydrogenated. In this example, the endocyclic double bond could be hydrogenated with high selectivity by carefully monitoring the amount of hydrogen consumed. Here, the starting norbornadiene contained two vinylic carbon-bromine bonds. Surprisingly, no reductive cleavage of these bonds occurred, and the unsubstituted double bond could be reduced selectively. Carbon-bromine and carbon-iodine bonds are readily cleaved by reducing agents in the presence of palladium or nickel. Allylic and benzylic halides are particularly reactive and difficult to hydrogenate without carbon-halogen bond cleavage. Nevertheless, it is sometimes possible to reduce alkenes selectively by choosing an unpolar solvent, a low reaction temperature, or by deactivating the catalyst with some additive. In this example, the hydrogenation was conducted in pentanes and almost no reductive cleavage of the carbon-bromine bond occurred. When carbon-halogen bonds are cleaved by hydrogenolysis, even as minor side reaction, hydrogen halides are formed which cause a strong acidification of the reaction mixture. In large-scale hydrogenations, corrosion may become an issue. Therefore, if a given starting alkene contains both carbon-halogen bonds and some acid-sensitive functional group, it is usually a good idea to perform the hydrogenation in the presence of a base or some buffer to prevent acidification. Alkyl chlorides are more resistant toward hydrogenolysis than bromides or iodides. Here, a heteroarene with a chloroethyl group was hydrogenated, and after crystallization, the batch only contained 1.2% of the dechlorinated product. This is one instance where the starting material acted as a chelating ligand and deactivated the catalyst. Therefore, a large amount of catalyst was required, and starting material and catalyst were only mixed in the presence of hydrogen. If the catalyst and starting material were stirred together without hydrogen, the results were variable and irreproducible. This is an example of the hydrogenation of an alkene containing both an alkyl iodide and a benzyl carbamate. Despite the sensitivity of these groups, the alkene was hydrogenated first. A good yield of product resulted by keeping the reaction time short. Like the catalytic hydrogenation of acyl chlorides to aldehydes, the so-called Rosenmund reduction, also imidoyl halides can be dehalogenated by catalytic hydrogenation. Anyway, the hydrogenation of olefins, at least in this example, can be sufficiently faster to enable selective reductions. This example shows that it is possible to hydrogenate alkenes in the presence of aryl bromides without significant reductive dehalogenation. The carbon-oxygen bond of ethers can also be cleaved by hydrogenolysis. Strained ethers, such as epoxides, are particularly sensitive, especially if one CO bond is allylic or benzylic. Thus, if no hydrogenolysis of an epoxide is intended, harsh conditions or excessive reaction times should be avoided. Here, a triene could be hydrogenated completely in good yield without reduction of the epoxide. In this example, similar to the previous one, hydrogenolysis of the epoxide was prevented by partial poisoning of the catalyst with ethylene diamine. The starting epoxide of this example was particularly tricky because it contained both an allylic and a benzylic CO bond. A fair yield of product could, nevertheless, be obtained with platinum oxide as catalyst in polyethylene glycol as a solvent. Nitro groups undergo catalytic hydrogenation quite readily, in particular nitroarenes. Aliphatic and vinylic nitro compounds are, however, less reactive, and alkenes containing such nitro groups can sometimes be hydrogenated selectively. Here, for instance, the alkene obtained by condensation of an aldehyde with nitromethane could be hydrogenated in high yield without reducing the nitro group. Benzylic esters and ethers can readily be cleaved by catalytic hydrogenation. In this example, this unwanted side reaction was prevented by deactivation of the catalyst with diphenyl sulfide. This deactivation was, however, not sufficient to prevent the reduction of aromatic nitro groups or acids. Here, the palladium catalyst was deactivated by a chelating bipyridine. This catalyst poison enabled the selective hydrogenation of a stilbene without reduction of an aromatic nitro group or cleavage of a benzylic ether. Even olefins containing peroxides can sometimes be hydrogenated without reduction of the peroxy group. In this example, the hydrogenation was performed at -12 degrees Celsius for only 50 minutes, and a high yield of target peroxide was obtained. Let's now have a look at some potential side reactions. A large number of functional groups may be reduced during catalytic hydrogenations. Extensive optimization can therefore become necessary if a polyfunctional alkene is to be hydrogenated selectively. Here, for instance, when the starting allylic ether was hydrogenated with a palladium catalyst, cleavage of the carbon-bromine bond occurred, followed by hydrogen bromide-mediated decomposition of the orthoester. With platinum and a slight excess of triethylamine, both the aryl bromide and the orthoester remained intact, but extensive cleavage of the allylic ether occurred. This ether cleavage could be prevented by increasing the steric bulk of the silyl ether. With a triisopropyl silyl group instead of a TBS group, almost no ether cleavage occurred and the target product was obtained in 80% yield. Even furanes can be cleaved with hydrogen, as shown here. Thus, with highly functionalized starting alkenes, it is advisable to keep the reaction conditions as mild as possible to avoid surprises. Aryl halides may not only be dehalogenated during hydrogenations, but can also dimerize or undergo Heck-type addition reactions to alkenes. In this example, 4-chlorotoluene underwent extensive reductive coupling to a biphenyl as well as dehalogenation. In the presence of hydrogenation catalysts, primary or secondary alcohols can sometimes act as hydrogen donors and be themselves oxidized to aldehydes or ketones. Particularly sensitive are allylic alcohols, which sometimes isomerize so quickly that no complete hydrogenation is possible. Aldehydes and ketones are not reduced as readily as alkenes and may result as byproducts, as in this example. This is a further example of such an isomerization. Here the main product was a ketone. Another potential side reaction is the decarbonylation of aromatic or aliphatic aldehydes. Such decarbonylations usually require a high reaction temperature, as in this example, because the catalyst will be immediately poisoned by carbon monoxide. Aliphatic aldehydes, such as the starting material of this example, require still higher reaction temperatures. Despite the high concentration used here, no extensive inter- or intramolecular aldol condensation occurred, and the decarbonylated products were obtained in good yield. Here are some more examples from organic process research and development and organic synthesis. These publications contain many discussions of various problems and thoroughly optimized procedures. On this and the next slide, there's a selection of some recent examples of alkene hydrogenation from other journals or patents. You can also find these references in the description of this video. The next video of this playlist is about the homogeneous catalytic hydrogenation of alkenes. Soluble catalysts, mostly complexes of rhodium, iridium and ruthenium, are less reactive but more selective than palladium or nickel, and exquisitely well suited for asymmetric hydrogenations. Enantioselective hydrogenations are also possible with heterogeneous catalysts, but rarely attain the high enantioselectivities achievable with soluble catalysts. So long.